In this lesson, we'll look at how to apply the kinematics equation for a simple 1D motion. 1D or one-dimensional motion often refers to motion along one direction only. You can think of it as motion in a straight line, where the object will either move forwards and backwards, upwards and downwards, or leftwards and rightwards. In our case, we have a stone that's thrown vertically upwards at a speed of 5 meters per second from the edge of a cliff. Assuming that air resistance is negligible, calculate the time taken to reach maximum height, the velocity at t equals to 1.2 seconds, the position of the ball when t is equal to 2 seconds, and lastly, the total distance traveled when t is equal to 2 seconds. When the stone is initially thrown, it continues to move upwards until it reaches the maximum height, and then from there, it will switch direction and continue to move downwards. Throughout the stone's motion, weight is the only force acting. Therefore, its acceleration will be equal to g throughout. It's because of this that when the object moves up, it will slow down because the direction of motion is opposite to the direction of acceleration. And then it will actually speed up when moving downwards because the direction of motion is in the same direction as acceleration. It should be noted that the velocity will always be zero at any point where changes in direction occurs. In our case, this occurs at maximum height because it's at this point that our object will actually have to stop momentarily before switching directions to move downwards. As the acceleration remains constant throughout the motion, we know we can use any of these kinematics equations. But which of these equations will we use? It depends on what is given from the question. In part A, we want to find out the time taken to reach maximum height. Time is what we want to find out. The initial velocity u is 5 meters per second. The final velocity v is 0 meters per second because it is at maximum height. And then our gravitational acceleration is 9.81 meters per second squared. Lastly, the displacement is not something that we know. Neither is it something that we want to find out. So the rule of thumb would be to disregard any of the kinematics equation that has the unwanted variable. In our case, the last three kinematics equations will be disregarded, leaving us with only the first equation. Before we can proceed, always establish a sign convention to tell us which direction is assumed to be positive. In our case, it will always follow the initial direction of motion. Since our object was moving upwards initially, upwards is considered to be our positive sign convention. So right now, we would have upwards as positive, v equals to u plus at. We sub in the values, 0 equals to 5 plus negative 9.81 t. T will give us 0.51 seconds. Now, you may be wondering, why is there a negative sign for the acceleration? It's because our sign convention is upwards, but the direction of our acceleration is downwards. So since it's opposite to our sign convention, this one would be negative. Similarly, since our initial velocity u is upwards, is in the same direction as our sign convention, this will be considered as positive. Moving on to the next part of the question, which requires us to find out the velocity at t equals to 1.2 seconds, let us first identify all the variables involved. Our time t is equal to 1.2 seconds. Our initial velocity u is equal to 5 meters per second, whereas our final velocity v is what we want to find out. Our gravitational acceleration remains at 9.81 meters per second squared as before. And then our displacement is not something that we know. Our final velocity is what we want to find out, whereas our displacement, although it's unknown, is not something that we want to know. So in general, if you want to apply the kinematics equation, we by right should only have one unknown. If you have two unknowns inside the same equation, we will not be able to solve the equation. So right now, what we'll do is that when looking at the kinematics equation, we'll just disregard the equations that has the unwanted variable, which in our case is actually the displacement s. So looking at the kinematics equation here, we will actually disregard the last three equations because they have the unwanted variable for displacement, leaving us with only the first equation to use. If our sign convention is upwards positive, applying v equals to u plus at, we're gonna get v equals to 5 plus negative 9.81 times 1.2 after subbing in the values. Our final velocity would thus be negative 6.77 meter per second. Now, you may be wondering what is the significance of this negative here. This negative here just simply means that our velocity is downwards, because it's compared with respect to our sign convention. Our sign convention is that upwards is positive. So if we get a negative sign, it means that our velocity is downwards. This would actually make sense, because if you recall from the previous question, it took us 0.51 seconds to move all the way to maximum height. Now at 1.2 seconds, we've already gone past the maximum height. So we would actually now be moving downwards. So it is actually reasonable to say that our velocity is directed downwards, as being indicated by our answer here. For part C, we want to find out the position of the ball when t is equals to 2 seconds. Again, let's identify all the variables involved. Our time t is equals to 2 seconds. Our initial velocity u is equal to 5 meters per second. Our final velocity v is not something that we know. Our gravitational acceleration g remains at 9.81 meters per second squared as before. Our displacement is also not something that we know. When we are asked to find out the position of the ball, they're actually asking us to find out the displacement. The final velocity v is not something that we know, neither is it something that we want to find out, so it won't be considered inside our calculations. Looking at the kinematics equation, we will actually disregard any of the equations that has the final velocity term v inside. So the first equation is out, second equation is out, and the fourth equation is also out, leaving us with only the third equation. So applying it to our question here, upwards is our positive sign convention. We have s equals to ut plus half at squared. Subbing in the values, we will get 5 times 2 plus with half times negative 9.81 times 2 squared. So our final value would actually be negative 9.62 meter. Now, what is the significance of this negative here? It merely tells us that the position of the ball is below the starting position. The starting position is actually our reference point here. So when we originally projected the object upwards, right over here, this is our reference point, which is also our starting point. Because displacement is a vector, we have certain sides that we will consider to be positive, certain sides that we will consider to be negative. In our case here, we would say that anything that is above our reference point is going to be positive displacement, whereas anything that is below our reference point is going to be negative displacement. Now, looking at how the object moved, we know that when the object went from the initial position all the way to the maximum height, it took us 0.51 seconds. So it will be reasonable to assume that from the maximum position or maximum height to go back down to the original starting point, it will also take the same time of 0.51 seconds. So in total, for the object to move up and then back down to the original starting position, it will actually take a time of 1.02 seconds. Now at 2 seconds, we've actually gone past the reference point. We will actually be somewhere below the reference point or our starting position here. So the negative sign here is actually telling us that. For the last part of the question, we want to find out the total distance traveled when t is equals to 2 seconds. When it comes to the distance traveled, recall that there's a difference between distance and displacement. Distance refers to the total length traveled by an object irrespective of its direction of motion, whereas displacement refers to the distance of an object from a reference point in a specific direction, which is what we found in part C. Now for part D, when it comes to the total distance traveled, we know that the object was projected upwards towards the maximum height, and then from the maximum height, it went all the way down towards the point where t is equals to 2 seconds. Our total distance can actually be divided into 3 different segments. The first one will be from the starting point towards the maximum height, which we can label as D1, and then from the maximum height towards the starting position again, which we can again label as D1. They're exactly the same. And then from the starting position towards the point where t is equals to 2 seconds, we already found out from part C that is 9.62 meter. Let's label this as D2. From here, we can see that our total distance is going to be 2 times of D1 plus D2. D2 is already something that we know. D1 is the only one that is missing. So if we want to find out D1, we will apply kinematics equation for the motion of the object from the starting position towards the maximum height. But before we can do that, we need to first find out all the relevant variables. The time t is 0.51 seconds, which we found out from part A. And then our initial velocity u is 5 meters per second. Final velocity v is 0 meter per second. Our gravitational acceleration is 9.81 meter per second square. And then our displacement is not something that we know. This displacement is actually our distance d1 that we want to find out. Looking at the kinematics equation, we can actually use the second equation, the third equation, as well as the fourth equation, except equation 1, because it does not have displacement inside. Now, let's say we use equation 2 for our workings. If upwards is considered as our positive sign convention, S is equals to half U plus V times T. S is our D1, then half 5 plus 0 times 0.51 will give us the final answer as 1.28 meter. Now, if we were to repeat this calculation with the third and fourth equation, we will be getting back exactly the same answer. Now, for our total distance, we know that it is 2 times of d1, so it's 2 times 1.28 plus with 9.62, we're going to get the final answer as 12.2 meter. This is our total distance moved. Now, to recap, if the object moved upwards and then went back all the way down, this one would have been known as our total distance. But then if we consider the final position of the object from our reference point in a specific direction, this one would have been considered as our displacement. So be careful when you're asked to find out either distance or displacement.